Hi everyone, I'm Praveen Jayakumar and we are going to go on a journey through quantum physics and quantum computers. This is especially made for the Breakthrough Junior Challenge. So consider this 1 rupee coin. Let this be heads and let this be tails. I spin the coin and cover it so it's out of my view. Now I cannot tell whether it's landed at heads or tails. It's either of these two cases. So if the coin were a quantum particle, a quantum physicist would say that superposition of both the cases, that is heads and tails simultaneously. That is for the time that's not observed. Weird, right? This nature of quantum particles can be proved by Young's double slit experiment. So when light was shown on two narrow slits placed near the screen, he observed bands of light caused by interference. Now we can reduce the number of photons to 1 per minute and observe only the screen. Naturally, we would expect only one spot on the screen, as the photon has 50% chances to go through any one of the slits. But there were two spots as though the photon had passed through both the slits simultaneously. If we then place a detector at both the slits, like before, there should have been two spots on the screen. But suddenly, when the slits were observed, there was only one on the screen. Hence, as long as it's not observed, quantum particles exist in all the states and they are all superimposed. But when they are observed, they retain the normal properties. So this has far-reaching applications. The theoretical and close to reality quantum computers work on qubits, which are the superposition of both 0 and 1. That is normal bits. So as long as they are not observed, they are 0 and 1. So this can be used to decrypt encryptions like RSA, DES, AES, PGP, elliptical curve systems, etc. that are widely used today for digital signatures, for encryption of data, etc. So normal computers take decades to crack these ciphers by brute force method, whereas quantum computers can solve these in minutes. Most of the encryption systems depend on the difficulty of solving problems like discrete logarithmic problem or the prime factorization of large numbers, and these can be solved very fast by quantum computers. To understand how it can, here's an intuitive example. So when you use a normal key to try open a lock whose key is unknown, it will take ages to try all the possible keys. So imagine a quantum key which is a superposition of all the cases, like a key of clay, which when tried, each case is tried simultaneously in multiple worlds, that is the multiple world theory of quantum theory, and the case that satisfies the lock is returned in just one trial. It is as though the clay key fills the hole provided for the key and takes the shape of the correct key. So here's an example, another example to get an idea of the magnitude of the benefit. So you want to find the numbers between 1 to 2 power of 256 whose square contains a pattern like 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. So you need to try all 2 power 256 cases by inputting 256 bits each time to represent the number so it can be checked. So this is like solving nearly 10 power 80 problems, and this will take more time than the age of the universe, even if all computers in the world worked on this problem. So, but this can be solved by a quantum computer with qubits and just one trial where all 2 power 256 cases are simultaneously tried and the answer is returned in just one trial. It may take few seconds or a few minutes, not more than that. So this can be thought to be analogous to the 256 data encryption systems. Now 256-bit data encryption systems and 512-bit data encryption systems can be easily cracked by supercomputers, not normal computers. So 1024 still takes at least 6 months to be decrypted by a supercomputer. By the time the message will become irrelevant. I'd like to end this video with an interesting application of quantum theory, time travel. So some physicists believe that time travel causes many worlds to be formed and the different changes and different worlds are superimposed on each other. So for example, if you break something in the past and you go and change it again, so at your present time, both it's broken and it's not broken. Interesting, right? So it is superimposed. So all the different worlds are superimposed. So some physicists believe that when you go back and change time, you end up in a different world, like the multiple world theory of quantum mechanics. So it's kind of puzzling and it's not known which one is right. Obviously don't have time travel machines, right? So it's a world of possibilities. And the future is still uncertain. The future is still a superposition of all the possible cases. So start dreaming and change the world for a better future.